Howdy. This is Chapter 2, which is called One-Dimensional Motion. The video for this chapter is in fact broken into two parts. This is part 1. According to a Chinese proverb, even the longest journey begins with a single step. The long journey you are embarking upon will give you the tools to ultimately design complex systems and predict how they will behave. The basis of these tools are the laws of physics based on Newton's laws, and to understand these laws, you must know how to describe the motion of an object. The study of motion without regard to the cause of the motion is called kinematics, and in this chapter, the necessary elements needed to describe motion will be introduced. Since it's better to learn to walk before starting to run, we start by considering motion that is restricted to a line, an object traveling along, say, the x-axis. The study of one-dimensional motion will be broken into 3 parts, with each part the subject of a lecture. Part 1, the definition of the kinematic quantities. Part 2, algebraic equations obtained from these definitions, which will enable us to solve interesting or uninteresting problems. And Part 3, examples of such problems. In the first 3 pages of Chapter 2, the velocity and acceleration are defined for motion along the x-axis. Clearly, you must master the process of finding the derivative of a simple function in order to understand these quantities. If you successfully completed the relevant problems and exercises in Chapter 1, you know all the calculus you need for the present. It will be instructive to watch a video to get a concrete idea of what we are doing. In the video, we have a cart that can slide along a tilted, straight track. The goal is to describe the motion of the cart. To accomplish this, we start by defining the x-axis to be along the track. We could paint a spot on the cart. Since the cart is not a tiny point, it is really the position of that point which we will be describing. For the early part of this course, we will assume that all objects are small enough to be considered to be points. Later, we will worry about finite-sized objects. What we are after is x of t, where t is the time. We need to choose when we want to call t equals 0 in order to have t defined. Clearly, the best choice for t equals 0 is when we release the cart, so that's when it starts down the track. So we're now going to do an experiment where I release this cart. It's at a certain value, 1 meter from the detector. When I release it, it accelerates, goes down the track. That detector measures x, the position of the cart, at each 5/100ths of a second. And the x as a function of t will be recorded in an Excel spreadsheet if my assistant knows what he's doing. Okay, so when I say 3, I'm going to let go. 1, 2, 3. Now we have an Excel spreadsheet that has x starting at 0.05 seconds up until the time where it banged into the bottom somewhere here around 1.5 seconds. So all we want to analyze is from the initial time down to about 1 second. So we have x at all those different times, and now he is going to fit x of t with a polynomial between the point 0, 0.05, and 0.9 seconds. Could you do that for us? That's great. So the coefficient, he asked it to fit it with a quadratic formula, at squared plus bt plus c, and these are the coefficients. This shows the data, and you can see there's a gray area mapped out on the computer screen. That's because this detector only measures objects if they are more than about 0.5 meters away from the detector. Once an object gets too close, the detector stops functioning. If we call the origin the point where the detector is located, at the bottom of the track, then you can see that x starts at approximately 0.88 and decreases as the object gets closer and closer to the bottom of the track. We have to stop our calculations at about 1 second because at that time the object is too close and the detector stops functioning. The crazy part of the graph after about 1.5 seconds corresponds to the detector being tipped over and actually measuring the position of something else, possibly my head. The fitted curve, the polynomial, as you see, goes right through all of the data points, so we have a very accurate description of the function x of t. Given this data, where we can write, let's pick an arbitrary time, t equal 0.5 seconds, we can write the position at t equal 0.5 seconds, t equal 0.6, 0.7, 0.8, 0.9. We can now calculate the ratio x at t plus delta t minus x at t divided by delta t by letting this be x at t and these be x at t plus delta t for various values of delta t, 0.1, 0.2, 0.3, 0.4 seconds. Easily the most confusing part of calculus is this limiting process, and now we can, by brute force, take the limit of x of t plus delta t minus x of t over delta t as delta t shrinks to 0. When delta t is 0.4, the ratio of the change in x to the change in t in meters per second is minus 0.58, minus because it's going to the left. When delta t is 0.3 seconds, it's minus 0.57. Smaller value of delta t, minus 0.55. Smaller value of delta t, minus 0.53. In fact, if we took one more point in between x equal 0.5 and x equal 0.6, we would take the ratio and find that the delta x over delta t, as delta t gets as small as we can make it, is minus 0.52 meters per second. We have a polynomial fit to the curve between the initial time and the final time, and we found that x of t in meters is given by this. If we differentiate this using our formula, that d by dt of k t to the nth is n k t to the n minus 1, this should be the velocity. If we want to evaluate that at our time, 0.5 seconds, just plug in t equals 0.5, and we get that the velocity from our curve is minus 0.516 meters per second, essentially the same as what we get by taking the limiting process. Not only can we understand what is the velocity from the definition, but perhaps more important, we can understand what do they mean in calculus when they tell us the limit as something is going to 0. You should now be prepared for the first lecture on one-dimensional motion and should be ready for a quiz like problem 1 or exercise 3. These simply involve knowing how to get the velocity and acceleration from a given position as a function of time. In part 1 of this chapter, you should have learned the definitions of velocity and acceleration in one dimension. Gegum.